Okay. Thanks for having us here. My name's Ethan. This is Aaron, and today we'll be going over our paper, which is a novel approach to quantifying zone exits.
So zone exits were popularized in the early 2010s by the work of Eric Tulsky and Corey Schneider. And as they're a big part of the growth of hockey analytics. And in my work with the Waterloo hockey team, I was doing a lot of hand tracking of zone exits and noticed that it doesn't always catch the full picture, just giving credit to one player for the controlled exit. So take an example of a dump in, defenseman makes the recovery, makes the first forecheck or miss, makes a pass to a winger who's right inside the blue line. That winger takes one stride and they get the controlled exit, and the defenseman gets no credit. So we thought of a little approach by building an LSTM to predict zone exits that would be able to give credit to multiple players, which makes more sense in our opinion.
Yeah, so as mentioned, we use an LSTM, and that was the architecture we chose because it is perfect for the sequential nature of hockey. You can think of it like a box that takes inputs and then does operations on them in sequences, and then it will keep the more important data and over time lose the less important data that it finds through iterations. And then the way we optimized it was just we did simple grid search. So we checked each parameter in a range, and then it made random combinations of these. And through that, we optimized for the best performing model.
So what did we use to train our model? So we inputted list of events. So we'd start the list, we'd start appending events to the list as soon as the team in the defensive zone gets the puck, their first event. Then we'd also add the last two offensive team's possessions. Then we would continue appending until either an exit attempt or a turnover occurred. And then we would take this list of events and then put the correct tag on it, either a controlled exit, uncontrolled exit, or a failed exit. We only used 5v5 data and non-endgame situations. And we also did some data cleaning to ensure proper zone exit attribution. You can check out our code if you want to see exactly how we got the data into sequences and what we cleaned it, how we cleaned it.
Yeah, so in the end, these were the features we chose to use, and the only real changes we made were we like filled nan, obviously, and then we went through in event name and type and did embeddings on them. So what that means essentially is they create a vector space for them, and the more sequential events will be more similar in that vector space. So you'll have something like pass shot is a common sequence. So those will have more similar values. And then something like maybe shot hit might have a slightly different difference in their values just because they're less sequential in the nature of hockey. And this was our model's performance. If you look at the confusion matrix, you'll see that our model performed very well with uncontrolled and controlled exits, a little bit worse with fails, and then didn't do great with classifying the negatives. So I think that has to do with the fact that a positive sequence like a exit has a lot to go into it. Like you have to be in the right position, you have to make a good passing play or a good stick move to get out of the zone. Whereas with a fail, you just have to make one bad mistake, one bad pass, and so it's really hard to predict that in a sequential nature. And this is further shown by the metrics table. Our ROC AUC curve showed really high success rate for the positive values, but struggled a little bit with the negatives. And our accuracy of about 78% shows that we had a model that was quite a bit better than just guessing.
So based on a paper that was written in 2020 by Chattel, he predicted the amount of shots you can expect to get based on each exit type. So a controlled exit is worth an expected 0.38 shots. An uncontrolled exit is worth 0.16 shots, and a failed zone exit is worth 0.07 shots. So using that, we can put that into our model and then look at, say, event 3 in the sequence and calculate what's your expected shot value by multiplying the expected like 0.38 for a controlled entry by the probability that our model says you'll get a controlled exit. Then you can do that for event 4. And then you can calculate the difference in expected shots to see whether that player's touch either helped or hindered your team's expected shot value from a zone exit. So that's how we built that table on the left. Those are the 5 best players in the data set for helping their team generate shots via zone exits. And then if you take a look at this table here on sequence positioning, that means out of all the expected shot value generation where the changes happened in the values. A lot of it doesn't occur with the last event. It occurs between the 50th and 80th percentile of events in the zone exit sequence. So that kind of confirmed our initial hypothesis that, hey, the most important event might not be the winger just taking a stride over the blue line. It's the defenseman who did all the work in my initial scenario. So what do we want to do in the future? We want to take a look more at this player rating metric. Is it smart? Is it useful? Is it stable? Does it deserve some future research? We also want to improve the player rating metric. The expected shot value framework could definitely be improved upon. Like, does it really make sense to give a player 0.07 shots for a failed exit? Like, could we maybe incorporate the probability that the other team gets the next shot to make that better? And also, it would be cool if we could have full tracking data, so know where every player on the ice is, as that way we could start to maybe generate some insights on how off-puck movement or offensive pressure affects zone exit probabilities.
Yeah, so quick review. We used an LSTM to take advantage of the sequential nature of hockey. We predicted and quantified zone exits using player event data, and then we introduced new metrics that take into account the entire sequence rather than just the final plays, which is what hockey currently does as a binary exit stat. Thanks for listening. If you want to see our code, that's the QR code. And that's everything. Thanks, guys. Any questions?
I've done something similar actually from the Finnish league data, and I think like the results are quite like stable and repeatable at least there. So yeah, I think you're on the right path on finding something.
That's exciting to hear. I'm happy that makes me feel better.
No other questions?
The code doesn't, QR code doesn't work.
That QR code doesn't work? It doesn't work. Okay, I'll double check that, but it worked for me yesterday. I double checked it. That's weird.
I think, is there a link in the paper?
Yeah, there should be a GitHub link in the paper.
So the link in the paper doesn't work right now? This QR code was paper. In the final print, the link will work for the paper.
Okay, great.
Okay, thanks, guys.
Yeah.